Hi, welcome. My name is Junao Fatherland. Today, I'm going to discuss to you the system engineering. That is, the engineering of a system. In this topic, we'll discuss the very broad issue because system engineering involves many professions that involve combined efforts of design, implementations, and evaluation, and that what holds the key of development of a human-made system. The topics that I'm going to discuss to you are the following. First, the socio-technical system, the conceptual design, system procurement, system development, and the system operation and evolution. Before we discuss the system engineering, let us define first what is a system. The word system is the most commonly used English word language because it has many contexts. We have physical systems such as solar system, satellite system, information system, nervous system, and many more. We also have philosophical systems such as social system, religious system, gambling system, and there's a lot more. The common aspect of word system is came from its early meaning and the great word. A system is referred as a whole or a set that results when the number of things have been grouped together in a particular manner for a particular purpose. In system engineering, we define system as a set of interrelated components, that is what we call the system elements, that working together with interconnections or interactions, bounded with a clearly defined boundaries for its system to achieve a common set of objectives. A system has its mission. The purpose of that system is called its mission. The mission must be clearly stated by the business management and stakeholders. The mission represents the starting point of a design process. Mission provides the basis for the ultimate test of the system fitness for purpose. In a broader sense, the mission of the system is to provide solution to a business problems. In software engineering, software is not an isolated activity but is part of a broader system engineering process. Software systems are therefore not isolated systems but are essential components of a broader system that have a human, social, or organizational purpose. In example, we have wilderness weather system as a part of a broader weather recording and forecasting system. This include the hardware and the software, the forecasting processes, the system users, and the organization that depend on the weather forecast. There are several types of a system. First, we have the technical computer-based system. The technical computer-based system include the hardware and the software, but not humans or organizational processes. Second, we have the socio-technical system. The socio-technical system include the technical system plus people who use and manage the system, and the organization that owns the system and the set policies for their use. In system engineering, we commonly encounter the system procuring, specifying, designing, implementing, validating, deploying, and maintaining a social technical system. This concerned with the services provided by the system, constraint on its constructions and operation, and the ways in which it is used to fulfill its purpose. Software is now the dominant element in all enterprise systems. Software engineers have to play a more active part in high-level system decision-making if the system software is too dependable and developed on time and to budget. As a software engineer, it helps you if you have a broader awareness of how software interact with other hardware and software systems. Social and organizational factors that affect the way in which software is used. we have several stages of system engineering. We have the procurement, development, and the operation. In this particular stage, we first create a conceptual design. Conceptual design set out the purpose of the system, why it is needed, and the high-level features that the user might expect to see in the system, followed by procurement or acquisition. The conceptual design is developed so that decision about the contract for the system development can be made. It's either to acquire a new system or to develop a new system. In this particular, a development will take place. Development of hardware and software is engineered and the operational processes is defined. While our system is up and running, we can consider the system operation. Operation or the system operation is deployed and used for its intended purpose. Remember, we cannot consider a fully functional system if the system doesn't serve its purpose. In the stages of system engineering, first we have the conceptual design, meaning we are going to define the system visions and features. Okay, after we create the conceptual design, we have to decide whether to acquire a new system or to develop a system up to its deployment. There are several professional disciplines involved in system engineering. Just like what I've said, software engineering involves many professions that involve combined effort of design, implementation, and evaluation that what holds the key of development a human-made system. In these particular disciplines, we have the electrical engineering, electronic, software engineering, user interface design, ergonomics, mechanical engineering, civil engineering, architecture, and many more. Since we have different disciplines, we commonly have communication difficulties, meaning different disciplines use the same terminology to mean different things. This can lead to misunderstanding about what will be implemented. We also have differing assumptions. Each discipline makes assumptions about what can and what can be done by other disciplines. We also have the professional's boundary. The professional boundary, each discipline tries to protect their professional boundaries and expertise, and this affects their judgment on the system. Let's move on to socio-technical system. In this particular, we are going to discuss the socio-technical system as more holistic approach to the development of engineering projects that involve the interaction between the people and the technology. The socio-technical system is a large-scale system that do not just include software and hardware, but also the people, processes, and the organizational policies. The socio-technical system are often called as system of systems, meaning it is made of number of independent systems that is working together to form the socio-technical systems. The boundary of the socio-technical system are subjective rather than objective, meaning different people see the different system in different ways. To thoroughly discuss the socio-technical system, here is the example of the socio-technical system.
The development of engineering projects that involve the interaction between people and technology. But let's start by taking an example of how our traditional approach to the development of technology and social organization works. Take Bob and Alice. They're both web developers and they both work on the same website. But Bob is a back-end web developer. He eats databases for breakfast and spends his days crunching code. Whilst Alice is a front-end web designer, she makes words sing and graphics come alive in simple and user-friendly interfaces that people love. If every few months the site needs updating, and Bob works hard behind the scenes coding away. He then hands the project over for Alice to work her magic on. This works fine initially, but as the site grows with more employees being taken on, things become a little less straightforward. We soon have multiple people working on increasingly specialized areas of the site, with developers and designers often needing to interact and collaborate but finding themselves stuck in their separate departments. Bob and Alice's site now requires a more holistic and non-linear approach to overcome this stumbling block, as it has now become what we would call a complex socio-technical system. But what does this mean exactly? Firstly, it is complex in that it has multiple elements such as lines of code, databases, graphics, and so on, with all of these different things needing to interact and being dependent on each other's functioning. Secondly, it is socio-technical, as a website represents an interface between the technical domains of computer software and the human interaction. For the site to function fully, we need to design both areas to work together. When we look around us, we can begin to see socio-technical systems everywhere. Let's take another example. This is a subway station in Hong Kong. It represents a highly integrated set of diverse elements. From the residential area to the commuter center to the transport hub, it was engineered and constructed by a single company. The designers of this system needed to think not only about how the physical technologies would interact and work together within a confined space, but also about how the residents and commuters might wish to use the system for multiple different functions. The website and subway stations are examples of systems on the small to medium scale. As we enter the 21st century, many of the challenges we face involve macro-scale socio-technical systems, such as growing demographics and urbanization, with urban infrastructure companies now offering solutions that integrate power grids, water supply, transportation, and other utilities that must interface with thousands of people on a daily basis and have a strong influence on the social fabric. Or with respect to the environment, where nations must balance both social needs, technological requirements, and environmental considerations to manage and grow efficient and sustainable economies. So we can think about socio-technical systems then as an approach to overcoming the problems of optimizing either the social or technical.
So that is the socio-technical system. The structure of the socio-technical system is the inner core is the technical system plus the operational processes, bounded with the organizational policies and rules, the organizational culture, the organizational strategies and goals, as well as the national laws and regulations. A socio-technical system are used within the organizations and are therefore profoundly affected by the organizational environment in which they are used. Failure to take this environment into account when designing the system is likely to lead a user dissatisfactions and system rejection. The organizational elements of a system. One of the elements of the system is the processes. Meaning, if the process is changed, system may require changes to the business processes, so training may be required and significant changes may be resisted by the users. Next, the jobs. If the process changes, the job changes. System may de-skill user or cause changes to the way they work. The status of the individual may be affected by a new system. Next, the organizational politics. System may change the political power structure in an organization. Those that control the system have more power. And last, the organizational policies. The proposed system may not be consistent with the organizational policies. A complex system may include software, mechanical, electrical, and electronic hardware to be operated by people. System components are dependent on another system component. The properties and behavior of a system components are inextricably intermingled. This leads to complexity. Complexity is the reason why socio-technical systems have emergent properties, are non-deterministic, and have subjective success criteria. The emergent properties, the properties of the system as a whole that depend on the system component and their relationship. The non-deterministic, they do not always produce the same output when presented with the same input because the system behavior is partially dependent on human operators. A complex relationship with organizational objectives, the extent to which the system support the organizational objectives that not depend on the system itself. The emergent properties of the system as a whole is the properties of the system as a whole rather than properties that can be derived from the properties of the component of a system. These properties are consequence of the relationship between system component. They can therefore only be accessed and measured once the component have been integrated into a system. The example of emergent properties: reliability, repairability, security, usability, and the volume. Types of emergent properties: we have the functional properties and the non-functional properties. The functional properties, these appear when all parts of the system work together to achieve some objective. For example, a bicycle has the functional property of being a transportation device once it has been assembled from its component. The non-functional emergent properties are example of reliability. For example, we have reliability, performance, safety, and security. These relate to the behavior of the system in its operational environment. They often critical for computer-based system as failure to achieve some minimal defined level in these properties may take the system unusable. Because of the component interdependencies, faults can be propagated through the system. System failures often occur because of unforeseen interrelationship between components. It is practically impossible to anticipate all possible component relationships, so software reliability measure may give a false picture of the overall system reliability. We also have hardware reliability and the software reliability. Hardware reliability: what is the probability of the hardware component failing and how long it takes to repair that component. Software reliability: how likely is it that a software component will produce an incorrect output. Software failure is usually distinct from hardware failure in the software does not wear out. As well as the operator reliability: how likely is it the operator of the system will make an error. Failures are not independent and they propagated from one level to another. System reliability depends on the context where the system is used. A system that is reliable in one environment may be less reliable in a different environment because of the physical conditions, and the mode of operation is different. The non-deterministic a deterministic system is one where given sequence of inputs will always produce the same sequence of output. Software systems are deterministic system, or a system that include humans are non-deterministic. The socio-technical system will not always produce the same sequence of output from the same input sequence. A human elements. A people do not always behave in the same way. System changes or system behavior is unpredictable because of frequent changes to the hardware, software, and the data. Okay, we also have the success criteria. The complex system are developed to address wicked problems where there cannot be complete specification. Different stakeholders see the problem in different ways, and each has a partial understanding of the issue affecting the system. Consequently, different stakeholders have their own views about whether or not a system is successful. Let us move on to the conceptual design. Conceptual design, we are going to examine how business needs and stakeholder requirements translate into a system-level understanding for our requirement of our system. This understanding will going to tell us what the system needs to do, how will it needs to perform, and the system it needs to interact with in order to meet stakeholder needs and requirement. We also need to look at the system level synthesis where we make a high level design decision before reviewing our work in preparation for the core design effort associated in the preliminary and detailed design. In the conceptual design, we are going to investigate the feasibility of an idea and develop that idea to create an overall vision of a system. Conceptual design precedes and overlap with requirements engineering, may involve discussions with users and other stakeholders and the identification of critical requirements. The aim of the conceptual design is to create a high-level system description that communicates the system purpose to non-technical decision makers. We have the conceptual design activities. First, the concept formulation. We start by concentrating in business or organizational needs and what the result and requirement eventually what the solution might be. Business needs and requirements are after all what we might try to address. Understanding this is our starting point. Followed by understanding the problem. We then try to look at the relevant stakeholders within the business would like to achieve. We are going to discuss the stakeholders, how they do their work, what is and isn't important to them, and what they like to do, what they like and don't like about the existing system. And then, the next step is the system proposal. It is what many consider the start of the traditional software engineering process where we take the business and stakeholder needs and develop a formal understanding of the system level requirement and the potential solution must made if it is to satisfy the stakeholders and business needs. We also need to know what level of compliance the solution might exhibit or options that come or that came out, how much it costs and how long it will take to realize. We might also be interested in risk associated with the solutions and the longer-term issues such as sustainment and disposal. We will also conduct the feasibility study of the system, meaning is the system may solve our potential problems. The system structure development is upon completing these conceptual design activities, we will come up with the system vision documents. Let us proceed to the system procurement. System procurement means acquiring a system or systems to meet some identified organizational needs. Before procurement, decisions are made on first, the scope of the system budget, and time scales. The high-level systems requirement. Based on this information, decisions are made on whether to produce a system, the type of system, and the potential system supplier. What are the decision drivers for us to procure or acquire a system? Number one, the state of other organizational system and whether or not they need to be replaced. Next, the need to comply with the external regulations, the external competition, the business reorganization, at the same time, the availability of the budget. It is usually necessary to develop a conceptual design document and high-level requirement before procurement. You are going to need a specification to let a contract for a system development. The specification may allow you to buy commercial off-the-shelf system, almost always cheaper than developing a system from scratch. The large complex system usually consists of mix of these shelf and specially designed component. The procurement process of these different types of component are usually different. So we have several types of system. Number one, we have off-the-shelf applications that may be used without change and which need only minimal configuration for use. Next, we have the ERP or the configurable application system that have to be modified or adapt for use either by modifying the code or by using inbuilt configuration features such as processes, definitions, and roles. Last, we also have the custom system that have been designed and implemented especially for use. So we have three types of system procurement process. Number one, procuring on the off-the-shelf system, acquiring configurable system, or developing a custom-based system. We have some issues to discuss before procurement. Number one, the organization often have an approved and recommended set of application software that has been checked by the IT department. It is usually possible to buy or acquire open source software from these sets directly without the need of detailed justification. There are no detailed requirements and the users adapt to the features of the chosen application. Some of the shelf components do not usually match requirement exactly. So, choosing a system means that you have to find the closest match between the system requirement and the facilities offered by off-the-shelf system. When a system is built, especially, the specification of requirement is part of the contract for the system being acquired. It is therefore a legal as well as a technical document. The requirement document is critical and procurement process of this type is usually take considerable amount of time. For public sector system especially, there are detailed rules and regulations that affect the procurement of the system. This force the development of detailed requirement and make agile development more difficult. For application system that require change or for custom system that is usually a contract negotiation period where the customer and the supplier negotiate the terms and conditions for the development of the system. During this process, requirement change may be agreed to reduce the overall cost and avoid some development problems. Decisions made at the procurement stage of the system engineering process are critical for later stage in that process. Poor procurement decisions often led to problems such as late delivery of the system and the development of the system that are unsuited to their operational environment. If the wrong system or the wrong supplier is chosen, then technical process of the system and the software engineering become more complex. Let us move on to the system development. Usually follows System development usually follows a plan-driven approach because of the need for parallel development of different parts of the system. It involves engineers from different disciplines who must work together. System development follows a V model, meaning we start with the requirement engineering, technical, architectural design, requirement partitioning, subsystem engineering, system integration, system testing, and system development. Requirement engineering. Requirement engineering is the process of refining, analyzing, and documenting the high-level and business requirement identified in the conceptual design, followed by the architectural design, which is establishing the overall architecture of the system, identifying the components and their relationships. Then, requirement partitioning, meaning deciding which subsystem identified in the system architecture are responsible for implementing the system requirement. We also have the subsystem engineering, meaning developing a software component of the system, configuring off-the-shelf hardware and software, defining the operational process of the system, and redesign the business process. Next, we have the system integration, meaning system integration is putting together system elements to create a new system. And then system testing is testing the system as a whole. The whole system is tested to discovered some problems. And then system deployment is the process of making the system available to its user, transferring data from existing system and establishing communication with other systems in the environment. System operation and evolution. System operation. Operational processes are the processes evolved in using the system for its defined purpose. For a new system, these processes may have to be designed and tested and operators trained in the use of the system. The operational processes should be flexible to allow operators to cope with problems and periods of fluctuating workload. There are some problems in automations. It is likely to increase the technical complexity of the system because it has to be designed to cope with all anticipated failure modes. This increases the cost and time required to build the system. The automated system is flexible. People are adaptable and can cope with problems and unexpected situations. This means that you do not have to anticipate everything that could possibly go wrong when you are specifying and designing the system. A large system have a long lifetime. They must evolve to meet changing requirements. Evolution is inherently costly. Changes must be analyzed from the technical and business perspective. The subsystem will need to interact so unanticipated problems can arise. There are rarely irrational for original design decisions. System structure is corrupted as changes are made to it. Existing systems which must be maintained are sometimes called legacy systems. Factors that affect the system lifetimes. Number one, cost, loss of expertise, and then the replacement cost. Return of investment, risk of change, and the system dependencies. Proposed changes have to be analyzed very carefully from a business and technical perspective. Subsystems are never completely independent, so changes to a subsystem may be side effects that adversely affect other subsystems. Okay, so we have several key points of this topic. Number one, system engineering is concerned with all aspects of specifying, buying, designing, and testing complex socio-technical systems. A socio-technical system includes computer hardware, software, and people, and are situated within the organization. They are designed to support organizational or business goals and objectives. The emergent properties of a system are characteristic of the system as a whole rather than its component part. They include properties such as performance, reliability, and usability, safety, and security. Okay, that's the whole topic of software engineering. Again, thank you for your time. This is Junal Fadrilan. Thank you.